In this video, I'm going to discuss normal distribution. But before I discuss normal distribution, I want to review the effect of changing standard deviation and mean. So let's start with standard deviation. What happens to a data distribution as the standard deviation is increased? So for example, here we have some graphs that show us low standard deviation and high standard deviation. Obviously, you can see that as we move from the left to the right, that is when standard deviation is increased. Actually, when the standard deviation is low, all the data values are very close together. So you can say 1 when the standard deviation is low, all the data values are very close together. So when the standard deviation is low, all the data values are very close together. And also we can say that as the standard deviation increases, the data becomes more spread out. So okay, so those are two important observations that we can note from the effect of changing standard deviation. In the next graphs, we want to investigate what happens to data distribution as the mean is changed. For example, as you move from the left to the right, the mean is increasing. What's happening? Obviously, we can notice that as the mean increases, the center of the distribution is shifted to the right. So as the mean increases, so these are very important observation. As you'll see later on, it will help you to answer some questions. All right, I'll move on to, but before I move on to normal distribution, there are two questions here that just want us to look at. The first one is, which normal curve has a greater mean between these two curves, based on the observations that we made in the previous pages? Which normal curve has greater mean? Obviously, the one that's shifting to the right will be having the greatest mean, which will be curve A. So curve A has the greatest mean. And number two, greater standard deviation. So the greater the standard deviation, the higher the standard deviation, the more it's spread out. So basically, that will be curve B. Okay, so this is very important, how a normal distribution arises. Now, I'm going to use a real life situation here to try and discuss how a normal distribution can arise. Now, the following numbers are measured nose lengths. So this is somebody who has done an investigation on nose lengths, different people, right? Different students. So these are 60 students to start with. So this person measured the nose length of 60 students, and their corresponding calculations are analyzed in the table below here. So if we used 5 millimeter class intervals, basically, if you look here, this person used 5 millimeter class intervals, uh, centered at 30, 35, and 70. And they did all these calculations. So I'm just gonna explain using one of these classes. I'm gonna explain how these calculations are worked out. I'll use this example here, this one here, to show you how these calculations were arrived at. All right, so the first column is just class intervals. Second column is frequency. Of course, total frequency is 60 because the number of students who their nose lengths were taken was 60 students, right? 60 students. And 5 millimeter class intervals. And you can see that on the first column. Now, relative frequency, I explained this when I was yeah, when I was discussing continuous random variables. Anyway, relative frequency is equals to the frequency of each class. So basically, using the one that I've highlighted here. So relative frequency will basically be the frequency for that particular class that it's being considered there, which is 21, over total frequency, which will be 60 in this case. And if you divide that, you'll get 0.35. And then density length. So density length, I'll use a different color here. So density length is basically equal to relative frequency I'm running out of space here. Try to put it inside here. So relative frequency over class interval. Now, on that row that you're considering there, our relative frequency is 0.35. And our class interval is 5. Remember, these are 5 class intervals. So 5. And if you divide that, you get 0.07. And that's basically what you have there. So this is how these calculations were performed. Now, one thing that I want you to keep in mind is that relative frequency, basically, this one represents probability. All right? So relative frequency represents probability. And that's why you can see here that all these probabilities here, all these probabilities add to 1. If you round off that to nearest whole number, they add up to 1. So relative frequency basically represents probability. And I discussed this when I was discussing continuous random variables. But this is how this table was arrived at. Gives you an idea of what really is happening here. Anyway, if we move on, so suppose you represent that data in a density histogram, whereby the y-axis is the density and the x-axis is the classes that are being considered. Remember, we considered class intervals of 5. That's why you have um, those measurements. So our histogram will look, so density histogram will look something like this. Now, what if we measured nose lengths of 100 students? So 100 students. And then we decreased. So suppose we decreased the length of class interval on that histogram so that we really had small class interval, very small class intervals. So the intervals will eventually get so small that we could represent the probability distribution of X. Okay, we represent the probability distribution of X as a density histogram. So, but because they're so small, we'll end up with a curve. And that curve will look something like this. So on the y-axis, you have, it's basically a function. This is a function, okay? Because you're joining very small points, so you end up with a function. And one interesting thing here is 44 here, what you can see here represents the average nose length. So 44 represents the average nose length. So most nose lengths will be close to the average nose length, which is 44 millimeters. And the values that are farther away from the average, they become increasingly unlikely. Like somebody who has a long nose length or very small, you'll have a few of those people among many. So many such situations can be modeled using a normal distribution. So this is a typical situation whereby you can model this situation using normal distribution. So what we've noticed from this page is here, what we have here is a function. But what is this function? What really is this function? So what you're saying here is a normal probability density function is a function that models a continuous random variable x, all right? And that continuous random variable, for example, in this case here, the nose lengths here, they actually form a normal curve. And that's why you can use this function, or basically the normal distribution function, to represent, to model this data here that we have here. So the continuous random variable x follows a normal distribution if its probability density function is defined by this. So this function here would basically model this data here. All right, where this represents the mean of x and that represents the standard deviation of x. And these are called the parameters of the distribution. And we write that as in this form, and this is read as x follows normal distribution with parameters mu and mean and standard deviation, basically what you have there. So if the mean was, for example, 4 and standard deviation was something like 6, you'll say x follows a normal distribution with parameters 4 and 6. Anyway, characteristics of a normal curve. So I want us to investigate characteristics of a normal curve. And I'll use a calculator to do that. So this is an example. Let X denote the IQ of randomly selected Kenyan. Suppose X follows a normal distribution with mean 100 and standard deviation 16. Use your graphing calculator to draw the normal curve that is the distribution of X. So what we need to do first of all is go on to y is equals to, because I basically want to draw the normal curve. So y is equals to, and then to get the normal probability density function, press second variables, then you'll get the normal probability density function. Now our x value, we don't have a specific x value, so we want actually the graph to plot that for us. So just press X. The mean in this case is 100. The standard deviation is 16. Now I've pasted that onto y is equals to. So that's a function. I'm going to have to set my window so that I can get a proper curve. So I'll set my window to x maximum, I'll put it at 40. X minimum, I'll put it at 160. Y minimum, I'll put it at 0.0001. And then Y maximum, I'll put it at 0.028. All right. So if you graph that, you'll end up with a normal curve. And you can see this normal curve is very similar to what we have here. Okay. So what I will do is I will just find a way of snipping this so that I can paste it on my document. Or you can just sketch it. So some features that I want us to investigate on the calculator. So back to my calculator, I want to find what the mod is. Remember, mod is x value where the function is maximum. So second, calculate, let's find that maximum value. The same applies to the mean and the median, so that the mean, the median, and the mod will be at the maximum point of this function because the function is symmetrical. Even if you look at it, this is a symmetrical function. So basically the mean will be at the maximum point, the mod will be at the maximum point, the same applies to the median. So let's see what, so left bound, we have that. Right bound, we have that. And you can see that the x value at the maximum point is 100. So what you're saying here is this is y, x. So the x value here is 100. All right? And that is the mean. So we can see that the height of the curve is maximized as at x is equals to the mean. We can say that, I think I'll write it below here. So we'll say the height of the curve is maximized at x is equals to the mean, because the mean is 100. That's the maximum point of that function. The mod occurs at the same point. And the same applies to the median. So we can say the mean, median, and mod are equal in this curve. Another thing is, if you inspect, it looks like a bell. So you can say it's bell-shaped. And like I said previously, it's symmetrical. about the mean. So the mean is actually the axis of symmetry here. Um, the probabilities all add to 1. So the total area under the curve, which represent the probabilities, is 1. We discussed that when we are looking at continuous random variables. So this is actually a review of that. Another thing is that the curve approaches but never touches the x-axis. Okay, so you can actually investigate that using a table by looking at the table of values. Um, Another thing that we can notice is the curve is positive for all values of x. So the curve is positive for all values of x. Now, these are some of the properties of normal curve. Okay, so these are some of the properties of a normal curve. Um, I want us to investigate something else. Let us investigate the points of inflection. So points of inflection. Um, this will give you a little bit of a review of calculus. So points of inflection of this curve. And we know that points of inflections are the points where the curvature changes. So basically, back to our function, uh, what I mean here is the points of the curvature changes somewhere around here and somewhere around here. So basically, we can find those points by graphing a derivative of this function. If we can graph the derivative of this function, we know that at this point and this point will have maximum values, all right? Because here um, the function is increasing before it starts to decrease, and then here it's decreasing before it starts to increase. So these points here will be, if we can graph the gradient function of this function, then we'll have maximum values at this point. So that's the idea that I'm going to use to graph these functions. All right, so to graph the gradient function, what you need to do is I'll go to y2, just leave y1 with the normal curve that we graphed. So in y2, I'm going to graph the gradient function. So if you press alpha window, number 3, and then what I want, so d over dx, and then here I want to plug in y1 because I want the gradient function of the normal curve. So go to variables, y, and then y1, where x is equals to x, because we want a just function. We don't want specific values of the derivative. And then we might have to change the window. So x minimum, leave it at 40, maximum 160 is okay. And then here, let's go with negative 0.001. And then here, 0.001 as well. So then if you graph it, of course, since we've changed the window, you won't be able to see the original function, all of it, but you'll be able to see the gradient function. So this is the gradient function. And like I said, the turning points are the points of inflection. All right? Remember, those are the points where the curvature changes. So we can find those points. So what I'm going to do here is to just get one of these curves and just snip it. If I can snip this somewhere here, not that big. Yeah, that's sufficient. So, all right. And then I can be able, I'll try and find what the maximum point here and what's the minimum point here. So second calc, let me see, maximum, just gonna jump onto that. Left bound, right bound. So that's around 84. So I'll just label it on my, this is 84. Remember the mean is around here. The mean is, from what we had in the question, the mean is 100. Okay, all right. We want to find what this point is, the other point of inflection. Just want to make it clear. Somewhere here. So the other point of inflection we can investigate. Second calc. That's a minimum one. So left bound somewhere there. Right bound somewhere there. And you can see that's 116. Now, just purposes of, and by the way, the mean, I think it's somewhere, let me try and just put it somewhere that, so the mean is somewhere here. Let's put it somewhere there. So that is the mean. Now, if you try to investigate, what's the distance between these 2 points here? And what's the distance between these 2 points here? All right, what's the distance between these 2 points? Yeah, I wanted the yellow pencil. That's working. Let me see if it's working again. Good. So the distance here will be 116 minus 100, which is 16. So that is 16. And here as well, the distance is 16. And this is very important. So we can see from this that the curve has 2 points of inflection. So we can say the curve has 2 points of inflection at if this makes sense. So basically, remember in our question that we had initially, The standard deviation, right? The standard deviation is 16. And what we have here is really interesting. You know, the points of inflection are on opposite sides of the mean, and the distance between the two positive and the mean is 16 on each side. So 16 there. So basically what you're saying here is the curve has 2 points of inflection at the mean plus minus the standard deviation. On the left, you have to subtract 16 to get the other point of inflection. On the right, you add 16, you get the other point of inflection. That's really interesting. So, well, just to summarize these things, we can say that we have also noticed that from the example that the shape of any normal curve depends on the mean and the standard deviation. I mean, if you change these parameters, mean and standard deviation, you'll end up with different curves, right? Because these are the parameters that determine the type of function that you end up with. But it will still be bell-shaped. So the shape really doesn't change, all right? Okay,